Thank you. Thank you for the introduction. I am Yasushi. My name is Yasushi Okawa. I am an application engineer specialist for semiconductor parameter analyzer and the power device analyzer. So today, I'd like to introduce our newly proposed new method to characterize a gate charge of power devices using B1506A. First, let me talk about a background of QG measurement needs. Here is a brief explanation of QG gate charge. Gate charge stands for a charge injected to the gate capacitances to drive gate voltage up to the on voltage. Since gate current supplied from the gate driving circuit is limited, the gate voltage do not rise immediately. It has this kind of shape. And basically, QG is very important parameter because it is very common in device dataset. You can find QG characteristics in almost all of dataset of power MOSFETs and IGBTs. The reason why QG is so important is for conventional power devices like IGBTs and silicon MOSFETs, power MOSFETs. It is key parameters to find required gate driving capability of gate driver circuit. Because gate driver has to have enough current and voltage output capability to drive the power devices, power switching devices for converters and inverters. And for also switching timing like on time and off time can be estimated from QZ curve. And some papers said QZ data is more useful than existing capacitance parameter to simulate the behavior of this kind of switching circuit. And also, as we told in our previous presentations, it is also useful to estimate switching loss and the driving loss of the power devices like silicon carbide and gallium nitride. Since on resistance of gallium nitride and the silicon carbide devices are very lower than conventional silicon devices, driving loss and the switching loss will become dominant in total power loss of the device. And this is the example of extracted input capacitance of the power MOSFET derived from QZ curve. And this dotted red line shows a QZ CB curve measured by conventional LCR meter. Due to the transition from the off state of the device to the on state of the device, effective input capacitance has this significant increase peak during the transient from the off state to the on state. So it is in actual device circuit simulations using this kind of active capacitance, dynamic capacitance instead of static capacitance measured by LCR meter is more efficient. That's the reason why QG measurement is very important for power device circuit designers. And this is the brief explanation of gate switching converters. This is the simplified circuit diagram of DC-DC converter, and this is a circuit diagram of inverters. used for motor control. And these switching devices are controlled like this, and turn on and turn off repeatedly. And in the DC-DC converter, duty ratio of this switching determine the averaged output current of the converter. Also, for inverters, this switch is controlled by pulse width modulated control signal like this, and its output becomes AC signal like this. So, to design the converters or inverters, gate driving circuit is more important. It's one of the most important components to realize such converters and inverters. This is the example of gate drive circuit of the switching converters. It consists of two switches, FETs in this case, and to isolate switching gate driver from the digital controller, typically optical coupler is used. And also to turn off this device, switching device, fast as possible, gate voltage of this device is driven by minus gate off voltage to positive gate on voltage. And since the gate driving circuit itself has a certain amount of power loss, so total to make total power loss lower, it is also important to make a power loss of gate driving circuit too. So QZ parameter is it's very useful to get to design optimum design of this gate driving circuit. So this is the example of gate charge characteristics listed in the device datasheet. You can see the QZ curve with different on current, and here is the list of the QZ measured at a single condition. But as you can see in the datasheet, you can find only limited information about QZ, gate charge. And you can find the typical value only. There's no minimum and maximum value. So you cannot know the variation of QZ of actual device you purchases. And also, as I explained, gate voltage is driven from minus to positive, but the datasheet only describes a positive part only. And also, to evaluate a switching time at turn off of the device, turn off QZ curve at turn off state, turn off situation is also required. But normally, QZ at the turn on phase is described in the datasheet only. So, if user want to know the enough information, QZ information, to design their converters or inverters, it is necessary to measure QZ by themselves. Okay, so next, I'd like to share basic physics of gate charge. In JEDEC standard, gate charge curve is defined as these three slopes. One is one slope. This slope is determined by the input capacitance at the off state. During the after device is turned on, this slope is determined by the CISS, input capacitance of the power switching device, and this slope, this flat part is called a plateau gate voltage. This reflects the mirror capacitance during the transition from turn off state to the on state of the device. So let me explain about the first part, S1 part. S1 part, since this is the typical input, output, and the reversed transfer characteristics of power devices, at the off state, the capacitance is almost flat, and the CISS is dominant. And in that case, since device is turned off, drain voltage is kept BSS off voltage during this slope. So this slope is determined by the gate charging current and CGS, input capacitance, gate to source capacitance. After the turn on, since so BDS moves to the on voltage. It's a very low voltage, and it also becomes almost stable. And in this case, gate current is charging both gate to source capacitance and gate to drain capacitance. So S2 slope is slightly lower than the S1 slope. At the plateau part, the physics is pretty complicated. During the transitions from the off state to the on state, drain voltage is changed from the off voltage to the on voltage. And during this, voltage point moves here to here. The on capacitance is changing, increases. Also, charge stored in the gate to drain capacitance at the off state is ejected during this transition, and it increases effective capacitance, input gate to drain capacitance. It causes mirror capacitance. During this phase, gate charge is consumed to earn this discharging current. That's the reason why during this timing, the gate voltage becomes flat. Okay, so next let me talk about the measurement method of QG, gate charge. Here are three typical measurement methods of gate charge. One is constant current rod method. It uses FET as a constant current rod. It operated in a saturated area to keep drain current constant during the gate charge measurement. Another one is resistive load. Resistance is used as a load during the measurement. Another one is inductive load method. It uses a switching tester to measure gate charge. So in B1506A, we use this constant current method and resistive load method. And as you can see, if you want to measure gate charge at high voltage, high offset voltage, and high on current, it is necessary to prepare the power source which can output such high off voltage and on current simultaneously. That's the reason why the QG tester becomes big. And this is the examples of QG testing equipments. This is a lab setup, handmade setup, and consists of oscilloscope and current probe and handmade gate driving circuit. It is very complicated, and also it is very difficult to get reliable data from such handmade solutions. Another solution is switching tester. Switching tester can test QG because they have switching they can measure transient characteristics during switching. But as I explained, it must have a big power source. And it's very expensive too. Another solution is benchtop QZ tester, dedicated test equipment for gate charge. This kind of equipment this kind of QG tester has QG testing capability only. But also due to this size, it has very limited output power range, like 40 volt and 50 amperes. But still, it's pretty expensive. Okay, here is a summary of existing QG measurement equipment. First, it has very limited output coverage. Even if a switching tester is used, maximum voltage is limited at several hundred volt and several hundred amperes. Also, setup is very complicated, and if you want to do the current load measurement, you have to adjust the driving condition of current load FET, and also you have to change load resistance when you use the resistive load method. Also, since this kind of equipment uses a digitizer like oscilloscope, so accuracy is not as good as SMU, source measure unit, and it also does not have less resolution. For example, a typical oscilloscope has only 8-bit resolution, but the SMU has equivalent 20 bits equivalent measurement resolution. Okay, so this is the summary of key feature of QZ measurement on B1506A. Its coverage is much up to 3,000 volt and 1,500 ampere. It is extremely larger than other solutions. With this large coverage, B1506A can measure QZ of big size IGBT modules. For example, the coverage of QZ is 100 microcoulomb. It's very big. And also, usage is very simple. Just put the device to the module socket adapter or connect the device by cable. Then you can measure the QZ immediately by just clicking the measurement button. Also, as I explained, SMU has 20 bits equivalent resolution. And also, in addition to QZ measurement, B1506A has IB measurement capability and the CB measurement capability. So due to this multiple functionality, B1506A can calculate the power loss of the switching devices. Also, B1506A can swing the gate voltage from negative to positive voltage. Typically, the existing QZ test equipment can only swing voltage in positive area or negative area only. Also, the software of B1506A supports turn on and turn off QZ, both turn off and turn on and turn QZ measurement. Okay, here is a summary comparison with existing solutions. And as you can see, the gate maximum current and voltage of B1506A is extremely larger than other solutions. And also, gate voltage B1506A can swing from minus 30 to plus 30. And gate current is up to 1 ampere to drive a gate of big IGBT module, and QZ range is up to 100 microcoulomb. While others can only measure up to 500 nanocoulomb, 100 microcoulomb of B1506A capability can allow B1506A to measure big size IGBT, which cannot be measured by existing solutions. Okay, here is a brief explanation of newly proposed QG measurement method in B1506A. In B1506A, to realize such wide QG measurement coverage on this single box equipment, we have separated QG measurement into two parts, high voltage part and high voltage, low current, and high current and low voltage. Theoretically, this area is determined by the off-state, high voltage off-state, and this area is only determined by the high current on-state. And we can merge high voltage measurement results and high current measurement results to create the total QZ curve from high voltage state to high current on state. And this is the method to measure charge injected to the gate. We use MCSMU to measure gate charge. And during the QZ measurement, MCSMU is operated in voltage force mode with specified current compliance. And when starting the gate voltage, applying gate voltage to inject the gate capacitance, SMU reaches to the compliance, specified compliance. At the compliance, MCSMU moves to the I force mode, constant current mode, instead of the voltage force mode. During this phase, transition phase, MCSMU operated in constant current mode, and it can measure voltage and current simultaneously. Then, from the measured current in 2 microsecond sampling interval, we can calculate the gauge charge by integrating the measured current. After gate voltage reaches to the total on voltage, SMU goes back to the B force mode. So it can, MCSMU only apply the voltage, specified voltage from the off state to on state, and during the switching phase, it can measure gate charge. This multiple operating function of MCSMU allows to measure gate charge from negative gate voltage to positive gate voltage. Okay, this is the process to create total QZ curve on B1506A. First, QZ curve is measured by a high current unit, like ultra high current unit, 1500 ampere or 500 ampere, or HCSMU, 20 volt and 20 ampere or 40 volt and 1 ampere module. Then extract JEDEC-based QZ curve based on high current measured QZ. Then next, measure QZ curve by using the high voltage SMU. Since on current of high voltage SMU is limited by its output current capability, plateau voltage, this is gate voltage to determine the on current, is lower than the measured plateau voltage than high current unit. But total QZ is measured from offset. This offset voltage, it becomes larger than the QZ measured by high current unit. After that, same JEDEC-based curve is extracted. Then we can merge those two measurement curve results to create a total QZ curve by this step. So first, extend this S1 slope measured by HBSMU, because this slope is measured by, determined by the off-state capacitance. Then extend this plateau part to the cross point at the slope 2 measured by high voltage SMU, because length of the plateau part is determined almost determined by the high voltage measurement part. And after that, shift this S2 curve measured by high current unit to this point, because S2 slope is measured by input current at on state with high current unit. Okay, so next let me show you measurement example. Okay. So this is QG test adapter, and this is FET used as a current load. Oh, this one? No. Okay. So just first put this QG adapter to the B1506A. Then, today I'd like to measure QZ curve of this packaged device. This is IGBT. They put the IGBT to the socket. Then, okay, so this is the software on B1506A. Then click Gate Charge Measurement Software. And first, set the off-state voltage. In this case, the datasheet said it is measured by 200 volt, and the on current is 40 amp. You can pick these parameters from the datasheet of power devices, and also set the gate current in the 1 milliamp, and on voltage is 15 volt. You can also find this value from the device datasheet. Then click measurement button. So we get the QZ curve very quickly. And this is JEDEC-based extracted QG curve. And this is the QG curve measured by high current unit. And this is QG curve measured by high voltage unit. So when looking at the waveform, this is measured results by high current unit. Purple line is drain current, and green line is drain voltage. And red line, pink or red, is a gate voltage. And as you can see, on current during the measurement is about 40 amperes. The gate voltage of current load FET is automatically adjusted at 5.7 voltage to make on current at specified value. So users do not care about this kind of adjustment. It's quite easy. This is the result of high voltage part, and off-state voltage is 200 volt, and on current is just 8 milliamps. So by combining measured QZ curve with those two high voltage and high current unit, we can get the total QZ curve from 200 volt and 440 amperes very easily. And also, it is very easy to change measurement parameters. So click camera icon to capture this curve as reference and change on current like this. Then measure it again. So we can get the QZ curve with 100 ampere on current. And it is very easy to compare the QZ curve with different measurement conditions. When using existing switching tester or labo setup, it is necessary to adjust on gate voltage of load current FET or value of load resistance to change measurement conditions. But on the B1506A, it is very easy. It is possible to change measurement condition by changing the parameters here. So this is the measured result with increased off-state voltage. It's quite easy. And also, JEDEC-based QZ parameters are extracted automatically. So you can compare measured QZ data with device datasheet. Okay. Okay, this is a very simple demonstration of QZ measurement by using B1506A. As you can see, it is very easy, easier than any other existing solutions. I have demonstrated this measurement for various customers in Japan, and every customer very surprised for ease of use. And also some of the customers said the measurement result is well correlated with their QZ data measured by their own setup. Okay, so it is possible to change gate voltage from negative to positive. It is also possible to just changing the voltage sweeping range on the setting on the QZ measurement software. And with the conventional switching test system, the users has to separate QZ into two parts, off state and on state. It is very time-consuming process to measure two QZ curve for one devices, but on B1506A, it is very easy. And to measure non-packaged device like IGBT module, this QG test adapter has terminals to connect this kind of IGBT modules. These are the cables equipped with B1506A, and it has these alligator clips. And in this case, resistive load is used because current of this device is very big. In this case, here is a result example of IGBT QZ measurement. This is measured QZ. Total QZ is about 4 microcoulomb. It's very big. As you can see in the previous slides, the maximum QZ range of existing solution is up to 0.5 microcoulomb. So those equipments cannot measure this device, but B1506A can do. Also, the current is, in this case, current is 1,300 amperes, extremely higher than the existing solutions. And the voltage is also 600 volt, and it's quite high. So B1506A can measure this kind of big IGBT device with this benchtop solution, not huge rack and stack switching tester. Okay, so these are the basic key features of QZ measurement newly developed on B1506A. As you can see, it will make QZ measurement significantly easier than before. I think this really changed the situation. Currently, QZ is measured by only very limited users, especially I think users, the power device users normally do not measure QZ by themselves. Only power device manufacturers measures these QZ by their own setups. But to design appropriate optimum power gate driving circuit and to choose a power device which has a minimum power loss, it is necessary to know the exact QZ under the actual operating condition, operating voltage and current, and also it is also necessary to measure variation of QZ. And the B1506A can allow all of users to measure QZ without any special technique. Okay, so in next few slides, I'd like to explain how to calculate the power loss of the device, switching time and the power loss of power devices by using B1506A. Here is a power loss of the power devices. By increase of the switching frequency, the amount of driving loss and the switching loss increases. And so conduction loss is very simple. It is determined by the ohm resistance and ohm voltage and the duty ratio. This is the power consumption at the on state of the device. This equation is not correct. I'm sorry, please fix it. This parameter is not related to the frequency. So to evaluate the conduction loss, ohm resistance of the device is very important. These are the typical ohm resistance characteristics described in the power MOSFET datasheets. And also for IGBT saturation, collector to emitter saturation voltage is important to calculate the on-state power loss. Because it is calculated by the on current and on voltage. Another one is driving loss. Driving loss is power loss consumed at the gate resistances, including internal gate resistance of the switching device at the during the turn on and the turn off situation. And this is totally determined by the QZ. Simply, the energy consumed at these resistance is calculated by this equation, QZ and the gate voltage. So we can calculate driving loss by using this very simple equation based on QZ measurement. So next is the switching loss. Switching loss is the power loss caused by the drain voltage and the drain current. If there is switching time is very short, there is no power loss during the switching. But actual device has a certain switching time, there is a power consumption. At the load resistance, this is a simplified circuit diagram of a switching test system with load, inductive load. The estimated power waveform of drain voltage and drain current is described like this. And also QZ is calculated from this. The plateau voltage is almost end at almost at the end of the drop of the drain voltage. And also by assuming the simple RZ and the C series circuit, we can estimate switching time from the QZ curve and the RZ. So by using this assumption, we can calculate on time and off time by using total gate resistance, including external and internal gate resistance and the gate plateau voltage, and measured QZ during this phase. Also, it is possible to estimate switching off time from measured QZ curve too. With resistive load, waveform is pretty difficult. By increase of the drain current, the drain voltage goes down immediately. So the equation is slightly different from the inductive load. But the measurement is very, switching time estimated by the same methodology. So we can estimate switching on and turn on and the turn off switching time from measured QZ curve. Then we can estimate the power loss, driving loss of the switching circuit with resistible load. This is the example of switching time calculation based on QZ measurement. First, simply assuming the series of gate resistance and capacitance. And from the, this is the response of IGS and BG based on the series R1C model. From this model, we can calculate the switching time, input capacitance from measured gate charge curve, and also by using this extracted input capacitance and total gate resistance, we can calculate the switching time from the QZ curve with these equations. So, as I explained, to evaluate the total power loss of the switching device, including conduction loss, driving loss, and switching loss, it is necessary to measure on resistance from IB measurement and input internal gate capacitance from capacitance measurement, and also it is necessary to measure QZ. Since B1506A can measure all of those parameters with this single test equipment, B1506A is the only equipment which can evaluate the total power loss of the switching devices as a single benchtop test equipment. Okay, so these are the all of the